A sequence is just an ordered list of numbers. So for instance, you could have the sequence of integers. They start out 1, maybe 2, 3, 4, 5, and they continue on forever. If you want to start at some other integer, that's totally fine. So you could have a sequence that is -5, -4, -3, -2, -1, and so on. You could take a sequence of odd integers, 1, 3, 5, 7, 9, and so on, sure, or even some primes. Prime 2, 3, 5, 7, 11, 13, and so on. Or even you could take the sequence of digits that happen in a particular number. So like for instance, you could take the number 1/3. That sequence is kind of boring. 3, 3, 3, 3, 3, and so on. Of course, I've only shown you integers. You could have sequences of real numbers or rational numbers. So for instance, you could have a sequence that looks like 1, 1/2, 1/4, 1/8, 1/16, and so on. Of course, the typical term here is 2 to the n in the denominator, so 1 over 2 to the n, where n is some integer. I started out here with n equals 0, and n equals 1 rather, n equals 0, and continue on. And so in order to deal with sequences, it's quite convenient to give them some names and to work with them in a way that allows you to index any entry in that sequence. The entries of the sequence are called terms. So each of these are terms in the sequence. And this counter variable, like an n, that's called an index, or an index variable. Now, typically we will like to name our sequences. So for instance, I might name a sequence, call it A, and that sequence might be, like the sequence we just had there, 1, 1/2, 1/3, 1/4, 1/5, and so on. So the typical term is 1 over n. And if you want to refer to any one of the entries in your sequence, you might say something like, this term is the nth term in your sequence, and the way to do that is with a subscript. So this whole a sub n is referring to the term. The n is referring to the index. This is a general description of a term. And we might even have some specific descriptions of terms that we have as well. So for instance, A3 is equal to 1/3. That's this guy. Of course, you can start your index wherever you like. And the thing to think of is that sequences are kind of like programming, computer programming. And in fact, you might even say that computers were originally invented to compute sequences, or at least to compute the terms in sequences. But now, as any computer programmer will know, and if you're not a computer programmer, you will soon find out anyway, that keeping track of the index is something of a problem. Different computer programmers have gotten different languages that use different conventions for managing the index. The Fortran programmer, working on his state-of-the-art mini-computer, will of course index his sequences starting at 1, because that's what God intended. The Python programmer will index his sequences starting at 0, because that's what all the cool kids are doing. But the most flexible of all is the Ada programmer, who can index her sequences however she likes, provided she promises beforehand. Now, where is she? She was supposed to be here now.
Excuse me, sir. We're not at liberty to discuss Ada programmers right now, so if you could please continue the video. Thank you.
Sorry about that. Well, okay, let's go on to the next topic of sequences then, and that is the notion of convergence. And convergence of sequences very much is about limits. This is about limits as n, the index, goes to infinity. And it does not matter where you start your index, because as you go to infinity, you kind of lose track of your start. So note, starting index usually does not matter. But the point is that the idea of a limit is that as your index gets larger, do the terms in your sequence approach some particular value? There's a precise definition for a limit, and this is the sort of thing that terrifies calculus students all the time, but it's not too complicated. Here it is. Okay, it's a mouthful, but let's read it and let's break it apart. So L, it's some number, is a limit of a sequence. I'll call my sequence A. The terms are A, N being the index. L is a limit of that sequence if every time you pick some number that's positive, there's a capital N, which is going to be an index, that says if I pick some greater index, then the terms are closer than epsilon to L. Essentially what this means that you can capture the terms of your sequence. So for instance, let me give you a nice concrete example. So let's make my horizontal axis my n, my index, and let's take a look at the sequence. A(n) is 1 over 1 minus n. So we'll start here, n equals 1, 2, and so on. So when I start off, when n is equal to 1, this sequence starts off at 0. 1, it's at 0. This is n equals 1, 2, 3, 4, 5, etc. And let's say this value here is 1. Now at 2, it's 1 minus a half. So that's a half. At n equals 3, it is 1 minus a third, so 2/3. And then 1 minus a quarter, 1 minus a fifth, 1 minus a sixth, 1 minus a seventh, and I hope you can see that this kind of seems like this 1 is an asymptote. Which is to say, now let's use that definition. So pick an epsilon. I don't know. Let's pick an epsilon that's like here. This distance is epsilon. If I do that and trace out these lines, you will notice that all the terms after A3. So if epsilon is as shown, the n is 3. Because all terms greater than whose index is greater than 3 will be within that epsilon width band around 1, making L equal to 1. Now, there's a little bit of a trick there. I've done this for one value. The limit definition requires this to hold for every epsilon. So it doesn't matter what epsilon you pick, you can always pick such an n. If you can do that, you've got a limit. If you can't do that, you don't. All right? Now, intuitively, the easiest way to get a hold of these is to draw a graph. Draw a graph, because then you can pretty quickly see what's going on. So, for instance, let me give you a few sequences, give you a quick graph, and tell you then what the limit is. Sequence, graph, limit, if any. And one thing as a caveat is that plus infinity or minus infinity are allowed as possible limits. So for instance, we just did the sequence 1 minus 1 over n. The graph kind of looked a bit like this, and so its limit as n goes to infinity of a n is equal to 1. All right, cool. This is true for geometric-y kind of things. So what about the sequence bn, which is equal to 1 over 2 to the n? Well, this is an exponential decay situation. So if n is equal to 0, well, what happens is 1 over 2 to the 0. That's 1 over 1. So that's 1. And then you get 1/2, 1/4, 1/8, and so on. And so it kind of tends to 0. And you can see that right away from the graph. Now, the fact that the 2 to the n is in the denominator is really important for limits to exist. 2 to the n in the numerator goes the opposite. I've got 1, and then I've got 2, and then I've got 4, I got 8, and pretty soon I'm off the page. And you'll notice it goes on to plus infinity. Of course, you can go to minus infinity as well. I won't write an example like that. But let me write out another sequence. This is the nth decimal in pi. What's that? Well, I always forget exactly what the nth decimal place in pi is. So hold on a second. Let me get someone here who can tell you what the nth decimal place of pi is. Okay, found him. Here he is. Can you tell me the first few digits of pi? Say it nice and loud.
3.1415926535897.
Wow, okay. Is there any pattern, or do they kind of keep going kind of crazy forever?
There is a pattern, but they don't.
They don't repeat? Okay. All right. Thank you. So he said there is a pattern after all, because pi is an actual number, but they don't repeat, and it doesn't really stabilize out to any limit. So that limit of that sequence does not exist. Okay. Now you might ask, well, how do I find what limits of sequences are? Well, we're going to learn a whole bunch of techniques, but one technique that stands out as being one of the most useful ones, and I'm going to tell you to review right now, is L'Hopital's rule. Use L'Hopital's rule. So for instance, if I take the sequence, and I'm going to call this sequence E, if you take this sequence, say, what's this sequence? The limit of this sequence, the limit as n goes to infinity of En, is the limit as n goes to infinity, n over n squared minus n. If I use L'Hopital's rule, I'll get a 1 over 2n, and you will notice right away that as n goes to infinity, that denominator gets really big, and you get 0. So sometimes L'Hopital's rule is just what you need in order to figure out limits of sequences.